Thanks everyone for being here on lecture 3. So let me tell you a little bit about what I'll do today and recapitulate a little bit what we did yesterday. So yesterday we looked at equivalence via automata, and we looked at different ways to optimize equivalence procedures using bisimulation of 2 techniques. And today I want to basically switch gears a little bit and look at Kleene algebra as an algebraic framework and how you can prove equivalence using the axioms. And this might look slightly less practical, but I will make some comments at the end on how this can actually be combined with yesterday's lecture and yesterday's technique to achieve some pretty neat procedures. And just to say that tomorrow I'll spend the time talking about much more practical applications of Kleene algebra, and I'll spend some time describing a family of languages that are used in network verification based on Kleene algebra. So before I actually start with the material of today, I want to answer some questions that were posed on Slack, and I'll spend 5 minutes doing that just to sort of clarify something from a previous lecture. So someone on Slack, Sheng, asks what is going on in this diagram. So let me just draw the diagram. And I'm just going to define everything in the diagram so that we know what we're talking about. So this diagram is basically has on this side here an automaton. And as Sheng has pointed out on Slack, I never said anything about this automaton being finite. So in fact, this diagram works for any automaton, even if they are infinite. I will mention in a second where finite plays a role. But for now, this is some automaton. And this thing here is the, if you like, the automaton of languages. Which is the final coalgebra for this functor that we're looking at. So again, recalling that an element in this set is a language by looking at it as a characteristic function. So given a word, it tells me whether the word is in the language or not. The functions OL and TL are the semantic Jozowski derivatives. So OL takes a language U, and it just answers the question, is epsilon in U? If it's in U, returns 1. If it's not in U, returns 0. Whereas TL takes U and the letter A and returns all the words U such that AU is in U. So it basically returns all the words that start with an A in U and removes the A from that. The map L takes a state in the automaton and takes a word in A star and will basically, I mean, you can read from the commutativity of this diagram that this will give 1 if and only if W is accepted by S, which maybe you remember is the same thing as saying that O of SW is 1. And then the question that Sheng had on Slack, let me just pull Slack if I can. The question was, how does this diagram say anything about regular languages? And this is the detail I didn't show very explicitly. So if you now add finite as the restriction of S, and you look at the image of this map L, So you look at all languages that this map L would give you. So this is sometimes called an epimonofactorization. So you have the class of all automata with a finite state space. So you have all the automata here, and you have all the languages here. And you basically just look at the image of this map L inside the set of all languages. And you can show that everything in the image here is a regular language. So basically this I here is the set of regular languages. And that requires a little proof, but it's not very hard. And then the second question that Sheng had was whether this picture also exists for regular expressions. And the answer is yes. Why? Because the set of regular expressions over an alphabet A also have an automaton structure given by the syntactic Brozovsky derivatives. I forgot how we call this. I think we call this ORTR. So this guy is now again an automaton. And we have shown that if we take this modulo ACI, then it's actually a finite automaton. And so the image that we had in the previous slide can then be basically drawn completely. So you have the final algebra here, the automaton of all languages, onto which you're mapping the semantics. But you also happen to know that if you look at the image factorization, then this thing here in the middle is exactly regular languages. And that's where these two theories sort of join. Okay, I think I've answered all the questions. Let me see. Maybe if Sheng is on, he can tell me whether I answered the first two questions.
Yeah, he says that was helpful.
Cool. And then the third question he had will come up in a moment. So I'll talk about least fixed points in a moment. Okay, so this was comment from last time. So let's go on with going back to the axioms and to Kleene algebra. This is just a slide reminding something I said on the first lecture, that there's all kinds of practical applications of Kleene algebra in program verification. And as I said, tomorrow I'm going to spend the whole lecture talking about network verification using Kleene algebra, which is something that is not even listed here. So these are sort of older applications. So today, I want to focus a little bit on the algebraic reasoning. So here's again the list of axioms that come with Kleene algebra. So maybe you remember that the plus forms this joint semilattice. So it's associative and commutative, and it has a zero, and it's idempotent. And then the sequential composition has the structure of a monoid, so it's associative and it has a 1, and it also happens to have 0 as the annihilator. And sequential composition and plus distribute over each other. And then there's this notion of an order, a natural order on the Kleene algebra that is very much defined by using the plus. So A is smaller than B, if I can write B as A plus B. And then the star is basically set to be the least fixed point of the following equation that is depicted here. So first of all, there's these two equations that say that is a fixed point. And in my previous slides, I actually presented them as equal. It's actually equivalent. It doesn't matter whether there's an equal there or not. In these ones, it does matter. So in these ones, they actually hold for smaller or equal. If you would place an equal instead of a smaller or equal there, then you would be defining something slightly weaker. So these blue axioms, these axioms here inside the blue oval, they really say that the star behaves as a least fixed point. And if you have seen the definition of least fixed points, you will recognize the pattern. So it basically says that, you have a fixed point X, and this fixed point is built from unfolding P. So you're doing P, and you terminate potentially with Q. And basically, this implication says if X satisfies this unfolding equation, then X has to satisfy the fact that its solution is a star followed by Q. And then there are always two versions of this equation, because you can either unfold on the right or on the left. So that's sort of what makes the star, the iteration, a little bit more general than, say, a while loop, in which you can only unfold in one way. So in the case of the star, you can unfold on the right or unfold on the left. And so what is interesting about these axioms, this set of axioms, is that these axioms, these axioms, as they stand, so this set of, I don't know how many axioms there are. There's 4 and 6, 10, 12, 14. These 14 axioms are everything you need to reason about Kleene algebra equalities. And this is what I want to show you today. I want to show that if you want to prove an equality about two regular expressions, you will always be able to do it just using these axioms. You don't need anything else. Now let's look at some basic facts about the order, which will be important later on for some exercises, but also for the completeness proof. So the natural order is, as it is defined, is a partial order. So remember that the order is defined as A smaller than B if A plus B is B. And so this order is reflexive, and it's antisymmetric, and it's transitive. And the proof that in fact this is a partial order very much depends on the idempotency axiom. The 0 is the least element, and again, it is the least element because in Kleene algebra, 0 plus E is always E. And you can show that all operations of Kleene algebra, so the sequential composition, the star, the plus, are monotone with respect to smaller or equal. And there you need to use some of the other axioms like distributivity. So this is important for the exercise that I will have in a couple of slides. So this is what I explained before in terms of the star axioms, and here they are a bit more made explicit in red. So remember that we have these axioms both on the left and on the right, and you can check that if you take this, the left-hand side of this implication, and you replace the right-hand side, so this thing here, in the equation, you will see that this is basically, you can conclude that P star Q is the least solution to that inequation. And so basically this is saying, as I said before, that star is axiomatized in Kleene algebra as a least fixed point. And the reason why, you might wonder why on earth I keep insisting on this and why this is in a lot of the Kleene algebra papers and so on. Just one historical remark. One of the first axiomatizations of Kleene algebra goes back to Salomon. Oops. Goes back to Salomon in 66 or 67. And in his paper, he actually axiomatizes the star in a slightly different way. And he actually axiomatizes the star as what he calls a unique fixed point. And by doing that, it looks very reasonable, except, as it turned out later, it is an axiomatization that ends up not being algebraic. And what does that mean? So I've shown you a couple of lectures ago that many structures are instances of Kleene algebra. So in particular, a matrix over a Kleene algebra is a Kleene algebra, or the set of relations is a Kleene algebra. In Salomon's version of Kleene algebra, that was not the case, because the fixed point rule that he came up with had a side condition. And the side condition was unfortunately not true for many, many structures. And so in fact, Salomon's axiomatization is perfect if you are only interested in languages. So Salomon's axiomatization really focuses on languages only. But if you want to use Kleene algebra in other contexts where you might need structures like relations for verification, then Salomon's axiomatization has some drawbacks. And that's why I've spent a few slides in these lectures sort of pinpointing that the star in Kleene algebra is axiomatized with an order, and it's a least fixed point, not a unique fixed point. So here's some exercises so that you can play around with the axioms a bit. I was thinking we can do this one in the next few minutes. There's a bunch of other ones here which already appeared in the first lecture, but since we didn't do them, I brought them back. Here, exercise 2 is about commutative Kleene algebras, which sort of shows that in commutative Kleene algebras, you can reduce a lot of you can commute the actions, and therefore you can reduce the way stars work in an easier way. But let's focus on exercise 1.3. So this one. This is a rule that is called in many papers the denesting rule, because it basically takes a program with a star and a plus and writes it as a program without a plus. And let's think a little bit how one would prove that this is true just using Kleene algebra axioms. You could use the automaton method we saw yesterday, but I want to use some Kleene algebra axioms. Oh, I have the star in the wrong place. Okay, Billy, you're going to be monitoring the chat for this one. So how do we start such a proof? Who has ideas?
David's suggesting that the first step would just be, or wait, no, that might be in response to something different. I'm not sure. Yeah, okay, that was a response to something different. Never mind.
So are there some ideas on how we should approach this proof?
Not yet. Tuto was wondering if it'd be possible to show the axioms on the side. There are a bunch of them though, so maybe.
Can you share, let me see how we can do this, because I don't want to move away from this slide since I'm going to be writing on it. Can you maybe share a I think they are on my slides that I shared on Slack in the earlier, in lecture 1. My Zoom has just frozen. I don't know if it's frozen for everyone or just for me.
Yeah, you started cutting out a little bit, I think.
Can you still see my iPad screen?
We have first, yes, we can see your screen, and I tried to send a screenshot of the axioms that were in the first lecture to the chat, and we have, I think, a suggestion as something to start with.
Okay.
Prasanth suggested the first step might be just saying x plus y star equals x plus y star, and followed by x plus y.
Billy, can you repeat that? Because I didn't hear the beginning.
Okay. Prasanth suggested maybe rewriting the left side as x plus y star, and then an additional x plus y after that.
Like that?
I can't see it yet. It hasn't shown up. Okay. Yeah, that's what he suggested. Cheng is suggesting unfold the left side first and then distribute.
Okay. Let me see if I can stop my video on Zoom to see if it helps, because it's dragging a bit at the moment. Okay, maybe that helped. Let's see. Can you see my pointer?
Yep, I can see it.
Okay. Okay, so those are interesting suggestions. But before we go on with unfolding things, let's realize one point. So let me just go back a little bit before we continue. So we have two stars in this equality, and the axioms about the star, you have to remember, are about order. So the first thing we need to do, or one way to go about it, is that in fact we might want to prove two inequalities. So we might want to prove this side and then the other side. So let's look at this side for a second, and let's see what we can do here. So if you look at the axiom that allows us to use the star, you will notice that I can indeed use some unfolding. And so what I want to do here, so in order to prove this, I'm going to use a couple of observations that I already made about the order. So in particular, I'm going to use the following things. So remember that 1, the regular expression 1, is always below star, and it's actually below if I have anything with 2 stars. Oops, let's not use A's. If I have anything with 2 stars, then 1 is below this expression. Does everyone see that? So 1 is definitely below x star. Why is that? 1 is below x star because 1 is below 1 plus xx star. Okay? Or in other words, 1 plus x star is equal to x star. And 1 is also below, by the same reasoning, 1 is also below this other star. And because I said before that all operators are monotone with respect to the order, then I can combine that, and I get that 1 is below x star, yx star star. Now, I also have that x star, and now perhaps you start seeing where I'm going, y x star star is below x star y x star star. Why is that? Because, again, using this fact here, that x star equals 1 plus xx star, then I can basically plug an x star there. So I do have that x star is below x star for the same reason that 1 is below x star. And because the operators are monotone, then I can plug this instead of x star. And I also have that yx star, yx star star is below yx star star. Now I'm using the unfolding of this star. So you will notice that what I have here on the outside is the body of that star. And this is also below, because of monotonicity, is below x star, yx star, star. How did I put that there? Remember, putting a 1 here is okay, and 1 is below x star. So I can apply monotonicity there. So here I'm using the thing I mentioned a couple of slides ago, which is the order is very well behaved with respect to the operators. And now I have all of this, so I can put it all together. So in particular, note that I have a 1 here, I have this here, and I have this here. So actually, I can put together that 1 plus x plus y x star. So here I'm sort of collecting this x and y together. Y x star star is below, and now I take the sum on the other side, is below what? Is below 1 plus x star y x star star plus y x star y x star star. And this whole thing now I can fold, and I have x star y x star star. So you basically, we have shown one direction. We have shown one direction now by using properties of the order, basically. Now the other direction is a bit more interesting, and there we're going to use the axiom, actually, so the order axiom. So let's look at the other direction, which is going to give us a little bit more. Let me think for a second. For the other direction, what do I want to do? A star, B A star, star. Oh no, sorry. For the other direction, it's actually a neat trick, because you can, I don't know why I keep replacing x's by a's. So for the other direction, I'll just take x star y x star star, and I can now replace x and y by x plus y everywhere because of monotonicity. And when you do that, you can now see again by monotonicity that this thing here is below x plus y star star, and this is x plus y star. And now again, using the unfolding axiom, you have x plus y star star, and then there's another exercise that says that star star is the same as star. So then you're done. Okay. So as you can see, I mean, the reason for me to show you this exercise is twofold. One is to show you that you can prove some things about star, but the other is to also show you that a lot of these proofs, I mean, I've done these proofs hundreds of times, and every time I need to think really carefully how I'm going to apply the axioms. And in general, proofs with Kleene algebra axioms are much more, require much more ingenuity than proofs using automata, which really are a little bit more straightforward, because you just make the same moves all the time. Whereas with Kleene algebra, you have options, and the options that were being suggested at the beginning can be valid options to approach this proof. I did it in this way because it's the way I usually do it, but you can have different ways of approaching the proof. Billy, are there questions at this point?
I don't think so. Not right now. There was a question a bit ago by, let's see. There's a question a bit ago by Nick asking about the, so in your, I think he's asking about in those axioms regarding the star and order, he was asking about the equality version of the axioms. I think what he's asking is, does the equality version follow from the inequality version or no? But if those axioms were, was it q plus px is
Yeah,
less than
so
x, imply
the inequality version is a strictly stronger axiomatization. So the equality version would be the equivalent of what Salomon did, and it will be a weaker axiomatization. So it will not, when I say weaker and stronger, I mean the number of models of this axiomatization, so the things that you can instantiate as models, will be less than if you have the less or equal. Okay, so this is about proving things with the axioms. What I want to do for the rest of the lecture really is showing you completeness. So as I said before, the reason why these axioms are so powerful, this list of 14 axioms are so powerful, is that if two regular expressions are equivalent, then there is a proof using only these axioms. And this is a very strong statement because it says whatever you want to show about regular expressions, you should be able to do using the axioms. Now, the question is, how does one go about proving such statements? And the reason I want to go in detail through this proof is that you will see tomorrow that with slightly variations of the expressions, you can have very different languages. And as I said, tomorrow I will focus on this network verification language, but there's other languages that also have parallel operators for concurrency. I'll try to see if tomorrow I have a little bit of time to mention that. And there are languages based on Kleene algebra that look at restrictions, just at while loops and things like that. And in every single instance of these languages, there's always the need to actually show that the language you present and the notational semantics makes sense. And one way to show that is actually to go via completeness. So you have a language and you have a set of laws that this language should satisfy, and you are building the notational semantics around those sets of laws. So you basically start with the language and the set of laws, and then you say, my denotational semantics should be this. And the way to sort of prove that your denotational semantics is the right choice is to show that your axioms and your algebra with your axioms actually gives rise as free model to that denotational semantics. And this is sort of a technique that pops up a lot in different aspects of actually programming language semantics. And the proof I'm going to show you is very specific for Kleene algebra based languages, and it involves automata and so on. But in fact, the essence of the proof, so if you strip away the sort of details that are very Kleene algebra specific, the sort of steps of this proof can be applied to other languages. And completeness is the sort of result that once you've done it and you've seen it done, you sort of start getting a flavor for how you can do it in different settings. And that's why I decided in this course that I want to show you in some detail how the original proof of Kleene algebra works. And tomorrow I will try to comment on how we've adapted the original proof to other settings. And sometimes it seems like a simple exercise to adapt it to other settings, but in fact, a lot of the details are very intricate when you change settings. So it's just the template, the structure that is the same. And so it's worth sort of taking a step back and thinking, what is the template of a completeness proof for Kleene algebra? And so what I will show you today is the template that actually was used in the original paper by Dexter Cozen in the early 90s. There are some recent reworks of this proof. One of those reworks is using category theory. I have a brief description of it on chapter 3 of my thesis if people are interested. And if I have time today, I might show you how that works using an extension of the diagrams that we looked at in the beginning of the lecture. So let's look at the original proof. So what do we want to show? We want to show that if two regular expressions are equivalent, then there exists a proof using only the axioms that we've seen a few slides ago. And so the way the proof goes actually connects to the proof of Kleene's theorem that we looked at in lecture 1. And so the way the proof goes, and before we go here, let me show you this thing, which is perhaps a bit easier to go through. So we have two regular expressions, S and T. And how are we going to show that they denote, there's a proof denoting their equivalence? So we want to start with two expressions. And what do we know about these expressions? We know that they denote the same regular language. And what does it mean to denote the same regular language? Remember, by Kleene's theorem, it means that there exists an automaton that accepts that language. And so the way the proof goes actually makes use of that fact. So this is the sort of steps in the proof. So I start with expressions S and T. And what I know about S and T is that the language of S is the same as the language of T. And so what I'm going to do, the first thing I do, I build an automaton from S and I build an automaton from T. And the way the proof works, you naturally build a non-deterministic automaton. So you end up with an automaton NS and an automaton NT. And then we're going to determinize these automata and we're going to minimize them. And why do we want to minimize this automata? Is because we know the following fact. I don't know if I mentioned this back when we talked about Kleene theorems, but deterministic finite automata have minimal unique representatives. What does that mean? That means that for every language, there exists a unique minimal automaton accepting that language. And the way the completeness of Kleene algebra works is basically by using that unique minimal automaton to obtain a normal form for each of the expressions. So basically, the way the proof works is that these S and T are going to be sort of massaged into a normal form. Let's call it an expression R. And that normal form is going to be such that S is provably equivalent to that, and R is provably equivalent to T. And so basically, you use this intermediate expression as a helper for completeness. And that intermediate expression comes from the minimal automaton. Okay? What is the missing, what are the missing steps, and what really makes this proof quite involved is that this whole arrow going here, all these arrows, in order for this proof to make sense, you have to be able to realize each of these arrows using only the axioms. So you can't use anything else other than the 14 axioms that are there for Kleene algebra. And so the core of the proof is to show that each of these steps, which we know from the classical theory, can be realized using the axioms. So let's go back to the previous slide, which says some of these things in more detail. So just to check, Billy, are you seeing the slide that says proof?
Yep, that's what I'm seeing.
Okay, cool. I have the feeling that something is slowing down again, but perhaps I'm being overly cautious.
The screen did just turn black the moment you said that.
I see. Is it back on or not yet?
Not yet.
So on my end, I do see the screen saying proof on Zoom, and that's why I have a hard time figuring out when it's back, because on my end, I always see it on Zoom. But I wonder if it's because it's connected directly to my iPad. Okay, so it's back.
Yeah, I can see your circle.
I did not draw that circle. Maybe someone was annotating the slides. Are we being Zoom bombed? Okay, I'll continue. Do interrupt me if the screen goes black, okay?
Okay.
I will make some markings in red on the slide in a moment. So if you don't see markings in red, then you're not seeing what I'm doing. So as I said in the slide that I showed before, we're going to look at several steps of this proof in which we encode constructions we've seen in Kleene's theorem, but now using the axioms. So in particular, we have this construction of a matrix that represents the automaton of a regular expression. And this really goes back to Kleene in 56, which is what we've seen. Then the other thing we're going to look at, which I briefly hinted at in the first lecture, is the elimination of epsilon transitions. And at this point of the proof, we have a non-deterministic automaton accepting the language. And therefore, we're then going to look at determinization using the axioms. And we're going to look at minimization. And here we're going to use something called a Myhill narrowed relation, which I will show in a moment. And then basically, as I said, the completeness comes from the uniqueness of the minimal deterministic finite automaton. And these, for those who have seen other completeness proofs, is the same sort of equivalent to the construction of a normal form. Okay. So let's go through each of these steps. Hopefully, we have time to go through all of them. So let's remember a few definitions. I mean, this is not very different from what we saw in the first lecture, but it now uses matrices because we're going to be making heavy use of the fact that matrices over a Kleene algebra are a Kleene algebra. So an automaton, a finite automaton over a Kleene algebra can be represented by a triple in which U and V are the start states and the final state. So in the case of the completeness proof, I do need the start state. And A is the transition matrix. So the way it works, yeah, this is bad notation on my end. I should have used a different letter here because I've been using A for the alphabet and now I'm using A for the matrix. And I'm using sigma for the alphabet now. So sigma is the alphabet now. So the way it works, you have a matrix A, which is a square matrix that is indexed from 1 to n. So think of this matrix as telling me, so if I pick a row I and a column J, what I'm going to have here is going to be an element of my Kleene algebra, let's call it U, that basically tells me between states I of my automaton and J, I can go from I to J using label U, where label U comes from the Kleene algebra. So it could be a regular expression, it could be a relation, it could be anything from K. And then basically the vector U will be a row vector that tells me that has zeros and ones in it. And if it has a 1, it tells me that that index, let's say it's J, is an initial state. And dually for the final states, I will also have zeros and ones, and it basically will tell me which states are final, will have a 1. And you can show that the language accepted by this automaton is actually given by the expression U A star V. And again, this, if we look at automata for the free Kleene algebra, which is the algebra of languages, then what you have here is nothing else than the classical definition of an automaton with initial and final states. And this expression, you can work out the explicit definition for languages, and you will get precisely the usual thing. So, you know, a word is accepted if there exists a path in the automaton that leads to a final state. But this definition here, using elements of a Kleene algebra, is slightly more general. So it's really what you put inside this matrix here, or in other words, what you label your automaton with, can be an arbitrary element of a Kleene algebra. So really, this definition is a slightly more general version than the DFA definition that we looked at in the first lecture. And this slightly generalization is needed for the completeness proof. Okay, so this is the first definition we need. And here's an example on the classical side of things. So it's an automaton with 2 states, and it's not my favorite automaton, it's my second favorite automaton, which basically takes all words that have a B in them. Okay. And so the way this would be encoded in the definition that we saw before would be by a triple that it's depicted here. So basically the initial state is state 1, the final state is state 2, and then the transitions between 1 and 2 are depicted here. So from 1 to 1, I only have letter A, from 1 to 2, I only have letter B. But from 2 to 2, I have both letters A and B. So I add the regular expression A plus B. And then you can compute the star of this matrix. And you will see that this is the star of the matrix. And if you now multiply by the initial and final vectors, you end up with this regular expression, A star B, A plus B star, that basically accepts all words with at least one occurrence of B. Okay, so this is a sort of neat trick from Kleene algebra. Now, we are going to have to select from this class of automata some special subclass. And in particular, I mean, eventually we are walking towards computing the minimal automaton. And on the way to computing the minimal automaton, we're going to need something called a simple automaton, which is, so an automaton is simple if it can be decomposed in this very special form. And here you start seeing the shape of the normal form sort of arising. So an automaton is said to be simple if you can split its transition matrix into 2 classes of matrices. One that is J, that only talks about zeros and ones, and the other one, so A of A, also only talks about zeros or ones, but is composed with the letters of the alphabet. And so basically this thing here is sometimes referred to as respecting the fundamental theorem of languages. That basically, in some sense, intuitively, it says that you can split a language into having the empty word or not, and then its derivatives. Notice how we're pulling out each letter once. Okay, so you're really saying my transition matrix is very special. I can pull out each of the letters, and what I'm left with is a matrix with just zeros and ones. And an automaton is sigma free, sorry, not sigma free, epsilon free, if the matrix J is the zero matrix, meaning there are no silent steps in my automaton. And the automaton is deterministic if it is both simple. So basically this part here says there's for each A, there's exactly one transition matrix. So that's the deterministic part. And then if J is zero, then that's really completely deterministic. So it has no epsilon transitions. And you must have, so deterministic is not only that you have just one transition, but you must have exactly one transition. So you also have to require that the rows of the transition matrix have exactly 1, 1. So they cannot be missing, basically. And the automaton in the previous slide is an example of such deterministic matrix. And so at this point, we are ready to do step 1 of completeness. And step 1 of completeness is basically saying that the Kleene theorem that we had in the first lecture is a theorem of Kleene algebra. In other words, it can be written just using the axioms. And so basically what this is saying here is saying that that automaton, so for every expression, there exists an automaton which is simple, such that the expression itself, and this is very important to note that this thing here is Kleene algebra equality. So the expression itself is syntactically equal to the expression that you get out of doing this matrix multiplication. So what we did in Kleine's theorem that is different from what this lemma states is that we actually did this step. So this equation here, we did it semantically. We said for every S, there exists an automaton, and we built this automaton such that the language of S is the language of the automaton. And so this is the crucial difference between the proof we saw in lecture 1 and what we need here, which is a syntactic proof using only the axioms. And that's what makes completeness proofs more involved, is that you have to do everything just using the axioms. And this proof goes by induction on the structure of expressions, and I'll show you a couple of cases. So for the expression that refers to the letters, what you do, you just build your automaton. Remember that an automaton accepting a letter A looks like this. So you basically draw two states, and you just write the letter A. This is assuming that sigma is just A. If we have other letters, then you would have to do different things, but let's not do that here. And so that corresponds to this matrix. So I have two states, one is initial, one is final, and there's only exactly one transition in this automaton from state 1 to 2. And now, if I look at the definition of U A star V, this is what I get. And the star of this matrix with just an A in the second position is the same matrix again. And you get exactly A. So in the end, you have A equals A, and so you're happy. You don't even need to apply any axiom at this stage because it's just the same expression. Let's look at the inductive case. So for the sum. So you assume that you have two automata for which you've already proven that S and T are equal to that expression. And now you have to build a new automaton. And one way to build this automaton is to basically create a larger matrix in which, so basically this is the same as saying, okay, I have an automaton for S here. I have an automaton for T. And what I'm going to build a larger automaton in which the initial states can be anything that I did from any of these initial states. So basically the initial state vector just takes everything you had in S and everything you had in T. And the same for the final state vectors. So you just put one next to the other. And the transition matrix basically says these automata have no transitions between them. There's no interaction between them. Therefore, I just put zeros around the states interaction. So these are the states from S, these are the states from T, and I have zeros in the interaction part. And this is really a disjoint union of the two automata. And you can now compute the star of this matrix, and you can see that it will give you A star, B star. And then once you plug in the definitions of the vectors, you will see that you get exactly S plus T. So again, you just get the same expression. And for the sequential composition, it is a bit more complicated because you do have something linking the two automata. So the two automata, when you have the automata for S and the automata for T, you need to link the final states of S with the initial states of T. And that is done by using the final states of S, that's V, and the initial states of T, which is X. And so you build this matrix and you take as initial state just the initial states of S, and you take as final states just the final states of T. And now you can compute the star of this matrix, which is not A star, B star anymore because it's not zero over there. So you get something a little bit more complicated. And when you plug in the multiplication of these matrices, you can use associativity to basically recover ST. And I'm going to skip the star case. You can look at it later. But basically for star, you do something similar to the sequential composition, but you need epsilon transitions as well. So I hope you've appreciated that the proof of, let's say, Kleene's theorem syntactically is a little bit more involved. But once you accept this switch to matrices is actually not so different from what we had before. You just need to keep reminding yourself that you need to work using just the axioms and nothing else. So for step 2 of the proof, we need to eliminate all epsilons that we might create, in particular when we have the star rule. And so to eliminate epsilons, we need to show that for any simple automaton that we start with, there exists another simple automaton that has no epsilons. Or in other words, remember that the definition of a simple automaton is that you can split it into a sum of these sorts. And we want to show that if I start with something that has ones in this matrix J, there exists an automaton in which that J can be removed. And so basically what the proof is not so difficult. So you start with an automaton. So this is the automaton that has epsilon transitions. And you just split your transition matrix to have the part that is epsilon free and collect all the epsilon transitions into a matrix J. And then you're going to basically use the denesting rule that we proved a few slides ago. Note here how this is the denesting rule. The X plus Y star equals X star Y X star star. So here we're using a lemma. So it's not a Kleene algebra axiom, but it's a lemma that we have proved using only Kleene algebra. And using the denesting rule, you end up with an expression in which you can eliminate the J. Because what do you have? You can take the S to be the U times J star, and you can take the B to be A prime J star, and you can take T equals V. But the point is, J star is a matrix with just 0 ones. And when you multiply by a matrix that already is epsilon free, you end up with something that is epsilon free. And here, again, I mean, the only thing you do is select, you have a matrix that has zeros and ones, and you're selecting states from U to be the initial states of the new automaton. So this is how epsilon elimination works axiomatically. The third step was determinization, and then the fourth step was minimization. So we have 2 steps to go. Determinization makes use of a rule that sometimes is referred to in papers as the bisimulation rule. And basically it just says, if I have a non-deterministic automaton N, and that there exists a deterministic automaton D, which can be much larger. That's why this square here looks larger, to make the point that the deterministic automaton is potentially exponentially larger than the non-deterministic one. But I can go from one to the other via a matrix X here in the middle. And this matrix X is really capturing the subset construction. So is mapping this matrix X, when you multiply on the right in the non-deterministic automaton, is telling you which states are going to be put into the set that then becomes the states of the deterministic automaton. And then you can show that if you have such matrix X that allows you to determinize the automaton, which always exists, then N star is times X is also equal to X D star. And so the language, this basically tells me that the language of this deterministic automaton is the same as the language of this non-deterministic automaton. And minimization actually makes use of a similar principle, which is basically saying, but now the role of X is slightly different. What is minimization? Minimization is you take an automaton and you have to collapse certain states. So there will be states in your automaton that accept the same language. And you want to say that you have a matrix X that basically collapses those states, that basically makes those states that accept the same language the same. And so basically minimization can also be captured in this way, as we did for determinization and using this bisimulation rule. And the proof of this bisimulation rule is more or less straightforward using Kleene algebra axioms. And the last thing is, if I have 2 automata that are isomorphic, I should be able to go from one to the other. Meaning, if the difference between the 2 automata is the order of their states, then I can show that they are the same, basically by using a permutation matrix that permutes the names of the states. And this is basically, again, if you have 2 permutation matrices, you can then show that the language of the permuted automaton is exactly the same as the language of the automaton you start with. And this basically altogether gives you the proof of completeness. So you start with 2 regular expressions. They denote the same language, meaning they have the same minimal automaton. And you show that you can go into that minimal automaton using just the axioms. And then at the end, you might end up with slightly different minimal automata, which are isomorphic. So you just permute them. And you end up here in the middle with one representative of both minimal automata that you can use to basically show that there exists an expression R here that is equivalent to both. And therefore, they are the same. So you basically built a proof using constructions from automata theory. And this is how completeness works. And this, sorry, I'm already moving on to a different topic. And this strategy of starting from expressions and finding a normal form using their operational semantics, which is really what automata are operational semantics, is a strategy that works for different languages. It is part of these constructions are very automata specific, but there are analog constructions for other sorts of operational semantics of languages. And so this ends today's lecture, which was a little bit maybe heavy on the technical side, because I showed you a completeness proof, which is one of, in my opinion, one of the heaviest things one can show about a language. But I hope you got a glimpse on how you basically link all these ingredients that we've been looking at. So we've been looking at semantically at regular expressions using languages and automata. And then we have these axioms, and we would like to prove things just with the axioms, and you can bring these things together. And one thing I didn't have time to show, but I would like to mention, is that working module with these axioms can make proofs or equivalence checks via automata much quicker. And there's a really nice functional Perl by Scott Owens and some other people in Chicago, which I'll try to put on Slack, where they show that, when you're building automata from expressions, if you take some of the axioms into account, you can get very close to building a minimal automaton corresponding to an expression. And there's some neat up to techniques actually associated with some of these axioms that have been explored. And again, I'll put a reference on Slack for this. There's some cool stuff out there that I didn't have time to show. So I'll stop here in terms of completeness. And I promise that tomorrow's lecture is going to flip around, and it's going to be not technical, and it's going to be more of an overview of where we can go from here into other languages for network verification and so on. So I'll change gears tomorrow once again, and thanks for bearing with me until the end of this very technical proof. Billy, are there any questions?
Yeah, there's a couple. From a while ago, there was Ariel just asking roughly the decomposition of a simple automaton into a sum is not unique, right?
It is unique given the restrictions on the matrices, because you require J to be a 0-1 matrix, and then you require all the A of A's to be a 0-1 matrix, and they have the prefix with the letter A. And therefore once you put all those restrictions in place, that decomposition has to be unique. And that's what makes a simple automaton, is the existence of that unique decomposition.
Okay, there is another request for reference to the formal proof.
Yep, I'll put in, so what I'll do, I'll make a README of my lectures, and I'll put for each lecture a list of references.
Next, there's a question for Prasanth. Apart from automata, which you're referring to, what other kinds of operational semantics are there for proving equivalence of expressions?
So depends on, this depends on the expression language you start with. You can look at the relational semantics of regular expressions, and there's also a similar completeness proof, albeit the steps look a bit different. If you're talking about a completely different language, you might find yourself looking at trees as the operational semantics and classes of trees. And then each of these steps will look slightly different. It will be looking at finding a normal form for a certain tree that might be capturing the executions of a certain program in that language. But typically, operational semantics can be specified using, for instance, what is called structural operational semantics, can be specified using a certain format of rules that always give rise to a certain type of tree. And you can use those trees in the process of finding a normal form.
Let's see. Iris is saying that they didn't understand the calculation of A star from the example, but I don't know what example they're referring to exactly.
Might be the, sorry. Where is that example? Example. This example?
They can.
So yes, was my question. So I think that if you calculate the star from the matrix, do you mean like multiplication for many times?
Yeah. So yesterday I said that when you have a matrix with 4 elements, let's call them X, Y, Z, and W. The star of that matrix is exactly denoting all the paths in the automaton between these states. Sorry, I'm drawing it slowly. And so, for instance, so the star of this matrix is by definition. So how can I go from state 1 to state 1? Well, I can do X star followed by Y, W star, Z. Let me see if this is true. So I can do X star. So I can do X star and then Y, W star, followed by Z. Yes, and there's a plus there, plus.
Yes,
So
I see.
And
you
then,
do it for each pair of states.
Yeah, so for each pair of states, I write a regular expression that tells me the paths between them. And in this particular case, because of this matrix here, you will see that the Z here is a 0. So in fact, this thing is going to go away. And so I'm left just with A star. But
yes,
that's not the case, for instance, between 1 and 2 and so on. So basically, there's a fixed formula for the star of a matrix of 2 by 2. And then using that fixed formula, you can extend it to larger matrices.
Okay, yeah. So I think I was more wondering, like, how does it follow from the axioms then? So my feeling is still that you look at the automata, but maybe like the
Yeah, you're making a good point. So what I'm using here in terms of axioms is that if I have a Kleene algebra K, the matrices over K form a Kleene algebra as well. And that Kleene algebra is defined by taking as definition of the star that matrix. And that definition is syntactic. I recover it from looking at the automata because that's where my intuition comes from. But you can just take that as a definition. So it's a syntactic definition of the star for matrices.
That makes things clear.
So the way that you're writing out the star, that's the same form as block matrix inversion, right?
It's the same as, yeah, it is connected to block matrix inversion.
Right,
yeah.
I assume there's some fundamental algebraic reason for that.
Yeah, but for me, but this is a personal view on things. I always draw this 2 by 2 automaton, and then I can draw the formula. I can't memorize this formula. I have to write it down every single time.
Any more questions? People can unmute and ask them at this point.
Or on Slack, so that everyone can take a break before Ugo's lecture.
You've got one question on Slack already.
Okay, I will look in a second. I had to close Slack because it was sort of draining a lot of battery for some strange reason. But I'll open Slack immediately after this. And I think Marco is looking very seriously at me to make me stop because it's almost 30. It's almost half past the hour. I see you, Marco. I see you. Okay, thanks everyone. And I'll put on Slack some references, and I will make sure that tomorrow's lecture is more lightweight and chilled.